All right, so playing around today with the definite integral. All right, the definite integral. Visually, you can tell if you're dealing with a definite integral versus an indefinite integral, because a definite integral has a small change in notation. We put these little a's and b's. Now, these are numbers, and what we wind up doing is looking at, well, first let's look at the geometric interpretation of this. What the heck does this mean? All right. I said that there's plenty of backstory to the integral. I'm going to go into it. But at first, we're just going to kind of dive right into the definite integral, and we'll do some of the backstory in a little bit once we've kind of reminded ourselves, what is it that we're really doing. So if I have some function that is defined and differentiable over an interval, whatever that is, I'm going to say that that's where my a is, and that's where my b is. All right. Well, if I were to integrate this, what I'm doing is I'm looking for the area underneath this curve. Okay, so when we do the integration, we come up with a function and what we do is we evaluate this function and I should preface this by saying that where, if I were to integrate f of x, I get capital F. All right, if I took the derivative of capital F, I'd get lowercase f. Okay, this is the antiderivative of the lowercase guy. It can, and well, let's keep it back. And what we do is we evaluate it, and this is the notation. Okay. What we do is we evaluate this function at b and at a, and we wind up with all right. So the process is take an integral, plug in the upper bound, and then plug in the lower bound and subtract them. Let's do an example. Let's do one that we already know geometrically, that we know the area to. Let's do a simple one. Let's do a constant, a simple rectangle. And let's do y equals 2. And we're going to evaluate it from, here to there, where let's say this is 3 and this is 10, and that's 2. All right, so what are we talking about? We're talking about a rectangle of width 7 and height 2. Okay? So if we integrate this thing, we had better get an area of 14 if we do this right. Okay? So the first thing we do is we set up our equation and spit out Harold's gum. So f of x equals 2. Thank you. So let's integrate that from 10 to 3. Okay, it's the area under the curve. So when we integrate this, we now get 2x evaluated between 10 and 3. Just going to move this guy a little bit, give myself some more room. So now we have 2, substitute in the 10, 2, substitute the 3, gives me 20 minus 6, which is 14, which is what we had expected. Now, this becomes much more powerful when we're dealing with things that aren't so simple to do by geometric means. Some goofy curve, some weird shape. Right. So there are some geometric formulas that you might want to remind yourself of, or at least put them somewhere nearby handy. What?
How do you got the equals 2, 10, 3?
Yeah. I took the integral and got him. Right? And then I substitute the upper and then the lower.
Oh, the f minus f8.
Right,
Oh.
because, and I'm actually going to take a moment here to divert from normal issues here. If you think about this as, if I were to not have anything down here, and I would just to say, if I'm going to integrate, I'm going to plug in 10. My area would reality be this area from 0 to 10, right? And then I would subtract off that. You see, that's really what's kind of going on. You know, you're going from one bound to a lower bound. Well, that's the same thing as saying from the upper bound to 0 and the lower bound to 0. Okay, that's important. Let's do that. Let's talk about this guy. Oops, excuse me. Let's get some straight. Oh, well, there's a difference between distance, which is always positive, and directed distance. Directed distance is saying I'm saying that north is positive and south is negative. So I could say if I wanted to go 2 miles south, that would be represented by -2. That's only because we establish a formality saying this is positive, this is negative. Yeah, exactly, same idea. So let's take the function. Let's first. Ooh, this will be fun. This is 4. This is 2. And this is, call it 4. So first, let's find the equation of that line. So we have y equals my rise and my run. My rise is -4, my run is 2. Plus my y-intercept, which is 4. So y is equal to -2x plus 4. Okay. So, yeah, there might be some simple introductory stuff to do, going back to Algebra 1. But anyway, so this is my equation. And I'm interested in integrating between 0 and 4. And I want to see what happens. So let's first do this. We integrate -2x plus 4 from 0 to 4 dx. Okay. Do the integration, plug in my bounds, and roll. So I wind up with -2 times 1/2 x squared plus 4x evaluated from 0 to 4. We all agree that that's the proper integration. Yeah, I'm going to simplify in a second, but yeah, you see, this is because what we're doing is we're not looking for the family of curves. What we're looking for is that numeric value. So in this case, the C has been, in a sense, determined by the fact you're saying this numeric value from here to this numeric value to here. So simplifying, obviously, this boils down to just negative x squared. So if I plug this in, I get negative 4 squared plus 4 times 4 minus negative 0 squared plus 4 times 0, which yields negative 16 plus 16, which is 0. What happened? Because we know full well that that's not a non-zero area. And we've got this guy down here, too. So let's look at this for a minute and say to ourselves, what's happening? Let's change this just ever so slightly. And let's just do it from 0 to 2. And see what happens when we just go from 0 to 2. Excuse me. So I wind up with negative 4 plus 8, which is 4. Okay, that's fine and dandy. Let's see if we're right. This geometrically is a triangle, so we have the formula 1/2 base times height, right? So my base is 2, and my height is 4, which is the same as what we got when we integrated. If we were to do the same thing down here, let's go from the bounds from 2 to 4 and see what happened. What do you expect it to be? Negative 4. Okay. Values above the x-axis are positive values. Values below the x-axis are negative values. Okay. No, it's values on the left of the y-axis are still positive if they're above the axis. Okay. And now we wind up getting negative 4 squared plus 4 times 4 minus negative 2 squared plus 4 times 2, which equals 16, negative 16 plus 16 minus negative 4 plus 8. We wind up with negative 4 and negative 4. It should be more complete. Okay. So areas above the axis are positive areas. Areas below the axis are negative areas. And in fact, I did something here without actually showing the proof of it. What I did was I looked at an interval and said, you know what? I'm going to go ahead and break this guy up into into two sections. I started with an interval from 0 to 4. And I split it up into two intervals, one from 0 to 2 and the other one from 2 to 4, which leads us to an interesting property of a definite integral. If f of x is continuous and on oops, there we go. On an interval a to b, I think yeah, it needs to be hard bounded. Fine. I don't want to confuse people with my notation here, so if it's all right, I'm going to change this to C. So I'm just putting b somewhere in between them, and that means that I'm chopping my integral up into smaller pieces. All right. Instead of going from a to c, I'm going to go to a to b first, and then from b to c on. Question?
So if we knew, or we could see last about where they cross their axis, we would do this with time where we could look at the graph and we have to change political dots that where to break it up in.
Very often, if you know that you have a root in there, you would want to make sure that you are addressing the root. So, for example, the integral it's not like it's wrong when we go from 0 to 4 and get an area of 0. But we want to make sure that we understand what it means when we get that negative value out of there and why it happens. It would sometimes, in a sense, what you're doing is you're taking away. If you're saying that, like, how about this? That curve represents my profit. Well, at the beginning of the month, I was making money, and all of a sudden, I'm losing money every single day. But I shouldn't say that. I'm just not bringing in as much profit until this center blue dot, this B value right here. At that point, my profit and my loss are equal, and I'm making no money. So this represents all of the money I've made, whereas the height would represent my profit for a day, or a profit for a moment, okay? And the if on this day, whatever it is, I'm making this much money, and then on this day, day B, whatever it is, on that day, now all of a sudden, I'm not making any money. And now, if I go a little bit further, I might be bringing in money, but I'm losing more than I'm bringing in. My profit is now negative. And if I go all the way to here, I have lost all of the money that I gained prior, and I'm ultimately sitting at nothing. Okay? Question? Yeah, well, this one of the things I was talking about before at the beginning of the class was that there's a lot of backstory to this, and we're going to get to that. But I want us to be able to know what a definite integral is, and then we're going to dive in and see the mechanics behind it. Because when we go into that, we're going to be talking a lot about the summation notation, and we're going to be using that summation notation in further problem sets. Okay. Yeah. No, because the next property addresses it. If I take the integral of any function from 3 to 3, I'm looking at the area underneath the curve at a point, right? You know? What is the area of that rectangle? You know? It has no width. So in a sense, it has no area. You know? It doesn't... No, it would just be 0. I mean, in a sense, if you really wanted to go through the rigmarole of it, you would wind up having... Right? It would just vanish. What's that? There are things that are what are called trivial cases, like this. But it's trivial, but if we don't have it, then sometimes it makes it very hard for us to keep going and saying, like, you know, even answering Harold's question, what if B and A were the same number? Well, it would still hold because we've done the trivial case. We know what that situation now occurs, you know, what happens at that situation. Yeah. Right, but we can't just throw up our hands and say, nope, can't do it. We want to be able to say what that means. And since we have this situation, we can say, well, then it's 0. You know, so the trivial case may not be used every day, but it allows us to go into situations that otherwise we would have no idea what to do. Okay, here's another one that's very important. What do you think would happen if I flipped the bounds? So instead of it going from A to B, it's now going to go from B to A. Same area, but negative. You're going backwards. Right. If you were to actually evaluate this.
But if it was negative in the first place,
Sure. All right. But then this guy would be, if you integrated him straight. Right? And the only way that these two can be equal is if you have a negative out in front. Okay? So sometimes this is kind of useful. If you factor out a negative sign from your entire function, your entire integral, you can get rid of that negative sign by flipping the bounds. Okay? Or if you want a negative sign in there, flip the bounds. That's another way of doing it. Okay, so these are important properties of integrals. There are other properties of integrals that we'll explore as we get to them. But in the meantime, this is about as deep as we need to go. Not yet. Now, let's go ahead and find the, and deal with some specific cases, shall we? Let's do some, by the way, I mentioned that you might want to remind yourself of some important geometric area formulas, okay? Um, there is another one, but you're not going to necessarily need it. Um, okay, those are common area formulas that become very used, especially the trapezoid one. The trapezoid one is very, very, very useful because you wind up having functions that you can deal with like this. I mean, that is a trapezoid. It's because if we were looking at, say A and B, and this was a line segment, and we wanted the area underneath that line segment, this becomes base 1 and base 2, and that becomes the height. And we can use the trapezoid formula that way. So let's try one for giggles. You could, but sometimes it's nice to do it a different way. Verify your results. That is another thing that we're going to talk about. We're going to do some housekeeping about how grades are going to be dealt with in the next week as we begin thinking about our next test, which will be after Christmas break. I'm not going to give you a test before break. I might give you a quiz before break, but I'm not going to give you a test before break. And I would say that being able to justify your answers, come up with another way to solve the problem to confirm your answer, that's a very important thing, especially on the IB exam. They're really big at making sure that you understand what you're doing, and to say, hey, I not only did it by plugging it into my calculator, but I also did it algebraically, or I made a table and confirmed the results, or something like that. Being able to say, yes, I'm right, and here's why, Yeah. So, all right. I have put one of these on your next homework assignment. I will probably do something like it in an upcoming quiz or test. Okay, because this kind of a problem where I say, find me the area under this line from here to here. That tells me that not only do you know how to do it using calculus, but it also allows me to know that you can verify your results with a geometric method so that you can believe that what you've got is right, Sir? It's for the x value. So if I wanted to find, let's just call this f of x. If I wanted to find the integral from 1 to 7 All right. It might be useful if you were doing it algebraically, with calculus. Since this thing doesn't have a nice happy function to go with it, we can use. Wait, I need to lie to myself. This wouldn't be 4, would it? Because this has a slope of 1/2. So at 4, it would only be at 1. All right. It would have to be only 1. Otherwise, I wouldn't have the same slope, the right slope through everything, right? Well, let's break this up into smaller integrals. From 0 to 4 of some function, and from 4 to 7 of some other function. Okay, and we'll find out what those functions are. Okay, because we're not going to find one nice happy function that does it. Right. So we have, what is my equation here? 1/2 x minus 1. And my other integral, y equals 1. And now we can go through this. Is that, yeah? For which? Oh, it's the constant value. It's the constant y equals 1 on that point, if we look at the graph again. This horizontal line is the equation y equals 1. Yeah? Okay. And now let's evaluate. And we get 1/4 times 4 squared minus 4 times, plus 7 minus 4. So 16, 4 minus 4, which is 0, and 3. So let's confirm our results. Make sure that we know that this really flies. All right. If we think about this rectangle, it's got a height of 1. It's got a width of 3. So it should have an area of 3. Now, this is off scale a little bit. I should probably... It should be more like that. It's a little bit more accurate now. All right. In that situation, we have a rectangle of height 1, base of 2, height 1, base of 2, one above, one below. So that area, since both triangles are the same size, just one is above and one is below, it kind of makes sense that it would cancel each other out. All right. So you have to believe it. Okay. And if you can look at the picture, and if the picture can make sense with the values that you get, that's that feeling, that warm fuzzy feeling of, yes, I've got it right. Okay. All right. I'm sorry? It is just 3. All right. There are plenty more questions that I could ask about this thing, but Let's do an interesting one. Yes? I was asked, I charged you with finding the area from, oh, I should have said 0 to 7. I don't know why I said 1. From 0 to 7. I think I was just looking at the 1 when I was there. But yeah, it's going from 0 to 7. So I went from 0 to 4 and then 4 to 7. Okay. Interval. Well, no, but one's positive and one's negative, so one canceled the other out, you know? So that brings up an important point. How would we integrate an absolute value? Okay. So if I gave you this, say, or better yet, yeah, that's enough. Okay, and I was interested in looking at, say, from negative 10 to 10. All right. We will remind ourselves that this has a vertex that's not at the center, right? And if you can put the graph into your mind about what this would look like, and you're more than welcome to use a graphing utility, this guy has a vertex at positive 2, negative 4. So we are actually really interested in, I'm going to get rid of some of this real fast. All right, so what we have is two straight lines, but there isn't a really nice way to do this integral, so what we're going to do is we're going to split it up. Because really what we have is we have two lines now. We have this line, which is now, let's find an actual honest to God value for this. We have x minus 2 minus 4 is equal to y. So that splits into x minus 2 minus 4 is equal to negative y. And actually, no. X minus 2 minus, what? Fluffy. And we also get x minus 2 is equal to y plus 4 times a negative 1. No, because that changes the sign on my 4.
Yeah, before you got
Yeah, yeah. So I have two equations for my two lines. And obviously this one is the one with the negative slope. And that's the one with the positive slope. And you see, now that we've broken it up into two smaller pieces, we can integrate this guy from negative 10 to 10 by splitting it up into two pieces.
You do both from negative 10?
No, you would just go from negative 10 to 2 for this function on the left, and then from 2 to 10 using the function on the right. Because that's, because my vertex is 2,
Oh,
right?
figured that out.
It's a transformation of a function. It's shifted 2 to the right, just inside the grouping symbol.
No, I'm saying how would you figure out like that you're split?
It's because it's an absolute value function, and you know that absolute value is in effect two different functions with a value where they switched over. It's kind of like a piecewise. You know?
So the vertex will always be where you split it.
Yeah. So now we have the integral from negative 10 to 2 of negative x minus 2 dx. And we're short on time. We've only got a few minutes left, so I'm just going to burn through this real fast. And we wind up with negative 1/2 x squared minus 2x evaluated from negative 10 to 2 plus x 1/2 x squared minus 6x evaluated from 2 to 10. So now I have negative 1/2 2 squared minus 20. Strike that, 4. It's just a whole lot of algebra. It looks big and evil and horrible and nasty, but in reality, it's just arithmetic. So this just becomes negative 2 minus 4 minus 100 negative 50 plus 20. So I get negative 6 minus, rather plus 30. So 24. And then I get 50 minus 60 minus 2 minus 12. So I get negative 10, 10, negative 10 plus 10, which is 0, and that's my answer. It's 24. All right, I am posting a homework assignment. I didn't have enough time to write it. I can just write it down now if you want to take a picture of it. It will be due, you're going over a weekend, so let's just make it next class. There's not a lot there.
Okay.
All right, this episode of the Bronco Show has been brought to you by the Indefinite Integral and our studio audience.